Now I will start the second lecture of week 7 of this course. In this lecture I will start talking about lattice imperfections, and we will talk about lattice imperfections in crystals, and I will start the discussion on point defects in this lecture. So, week 7 lecture 2 will be lattice imperfections in crystals. Okay. So, we will just we have been talking about crystals and crystal structure, and we have sort of been focusing on the symmetries and the properties of a perfect crystals, but very often, in fact almost always, you find imperfections in crystals. Okay. And each of these imperfections leads to its own important phenomena. Okay. So, it is good to understand what are the kinds of imperfections that you can have and what kind of effects they can have. Okay. So, there are several different ways to classify these imperfections. So, I will look at one way which is very convenient for us. Okay. So, we can think of the defects as point defects or line defects or planar defects or bulk defects. Okay. And then I will also mention that there are things like lattice distortion, non-stoichiometry and partial occupancy, etc., which can be put into one or more of these defect categories. Okay. So, point defects, okay, an example is there could be a vacancy where one atom is just missing. Okay. You have a perfect crystal, but one atom is just missing. Okay, then that would be a vacancy, and that would lead to something, that would lead to a point defect. You could have an interstitial where an atom is found at a site that is not the standard site in a perfect crystal. It is found in some other site which is not a perfect site in the crystal. There could be impurities, there could be foreign atoms that come, and then I will talk briefly about F centers. Okay, so these are very specific. This name is specific to ionic crystals, and I will briefly introduce that. Line defects, the examples of line defects are dislocations and disclinations. Okay, again I will talk briefly about these. Line defects are actually very they play a very important role in the mechanical properties of the material. Okay, so when you try to bend or try to strain a material, okay, then these dislocations would turn out to play a very important role. There can also be what are called what you can classify as planar defects. These are things like grain boundaries or stacking faults. And then there can be bulk defects. So what I mean by a void here is that there are a whole bunch of atoms that are missing. Okay, you can have voids, you can have cracks in the crystal. You could have a collection of atoms forming something like a little precipitate within the larger crystal. So if you have a crystal of one material, okay, that I am showing in blue, you could have some region where there is a precipitate or some sort of inclusion of some other material. Okay, so this green region is a different material. Okay, I am really thinking of a very large crystal here. Okay. You could have things like lattice distortions. You could have non-stoichiometry we will see examples of these as we go on in this course. You could have partial occupancy, like some sites are only partially occupied by atoms. Okay, these would lead to other kinds of defects. Okay, let us talk a little bit about the point defects. Okay, and I will do a few examples of very well known point defects that you might also be familiar with. Okay, the first one is Schottky defect. Okay, Schottky defect is actually if you had an ionic crystal like let us say NaCl, okay, then Schottky defect would be defect would correspond to a Na plus and Cl minus missing. So, a pair of Na, so one sodium plus and one chloride ion missing. So, that combination would be a Schottky defect, and the point is they need not be right next to each other. If you had a pure metal, okay, a single element, okay, then the Schottky defect would be a vacancy and surface atom. That means an atom leaves its site inside the crystal and goes to the surface. Okay, so that would be an example of a Schottky defect. Okay. In sodium, you can imagine that somewhere one sodium is missing and one chloride is missing somewhere else, okay, and they together form a Schottky defect. Okay. Just to remind you, the chloride so if I show the sodium atoms in blue and the chloride atoms in green, okay, then the sodium chloride is this rock salt structure, okay, which is essentially you can think of it as two interpenetrating FCCs. So, the sodium atoms will form an FCC. I am just showing in one plane, and the chloride atoms will also form an FCC. Okay, and if you extend this, you will get in all directions, okay, you will get the sodium chloride structure, the rock salt structure. Okay. Now, if you had some atom that is missing, say for example, if this sodium is missing and some chlorine, let me show it somewhere else, that is missing a little far away. Let us say the chloride and here is missing. Okay. So, then this missing sodium and this missing chloride, so this pair would form a Schottky defect. Okay. So, this would be a Schottky defect, and the point is that this sodium ion is positively charged, the chloride ion is negatively charged. Okay. So, if you have one sodium and one chloride missing, then the crystal as a whole will be neutral. Okay. So, the neutrality of the crystal is maintained. Okay. So, both you can see that both charge neutrality and stoichiometry are maintained. Are retained. Okay. And these Schottky defects actually play a big role in electrical conductivity. Okay. And so Schottky defects are much studied in the area of when you are looking at conduction through materials, then the Schottky defects actually play a role there. Okay. What about Frenkel defects? Frenkel defects are different kinds of defects. These are these are interstitials. Okay. So, for example, the canonical example of a Frenkel defect is the silver chloride. So, you have Ag plus and you have Cl minus. Silver chloride, this is another ionic crystal which also crystallizes in the rock salt structure. Okay. So, it also forms a rock salt structure. So, if you just show it in 2 dimensions, so one of the defects that is observed is when one of these silver atoms, okay, they go to an interstitial site. Okay, so you could have maybe this silver atom has left its site and it has gone to some site, let us say somewhere here. Okay. So, this combination of, oh, I should show silver, sorry, I wanted to show the silver. Okay. Let me also emphasize that chloride, being a negatively charged ion, is actually much bigger than the silver. Okay. And then in this case, a silver, now the Frenkel defect corresponds to a silver atom leaving its site. Okay. So, it could leave its it leaves its site and goes to some interstitial site. Okay. So, this would be an example of a Frenkel defect. Okay. So, this is a vacancy interstitial pair. Okay. So, vacancy interstitial pair, this is a Frenkel defect. Okay, in particular this is referred to as a cation Frenkel defect, because silver plus is a cation and the cation is forming this Frenkel defect. Okay. Now, there is another defect again, that is you could also form Frenkel defects in pure metals. Okay. It could also happen in pure metals, okay, where you just form a vacancy interstitial pair. Okay. So, this can also be present in pure metals. Another kind of point defect, which is traditionally, these are referred to as color centers. Okay, these are seen in ionic crystals. Okay, and this is these are often non-stoichiometric. Okay, in the sense, suppose you take sodium chloride. Okay, and you put sodium vapor. You put it in some vapor of sodium. Okay. So, sodium, you take sodium gas and you pass it over sodium chloride. Okay. Then you can get something like a crystal that has a slightly different stoichiometry. So, the stoichiometry, so delta greater than 0. Okay. So, it is some small fraction, it is delta is some small number like 0.01 or 0.02. Okay. And in this case, these excess sodium atoms, okay, will go to interstitials, okay, and the excess sodium will lead to colors. Okay, and they are called as, for example, they are called as F centers. F stands for F center, or there is in the F comes from the German word Farben Center. Okay, so that's an F center or a color center. Okay. Similarly, this so essentially these excess sodium ions, okay, they will actually lead to a change in the color of the sodium chloride. Okay. So, the sodium chloride crystal will actually show a different color in the presence of these excess sodium ions. Okay. There are other centers you can get. I mean, there are a number of these color centers. So, for example, if you put this actually looks, the color of this is actually greenish to yellow color, depending on how much sodium is there. Okay. You can also get, for example, in K plus KCl, KCl. So KCl with K vapor, you get violet color. Okay, and actually it is not very hard to show why these the presence of excess charge, okay, will lead to these colors. So there are other defect centers. Okay, so this just as you have an F center, you can have things like I'll just list the names of some of them. You could have something called an F prime center. Okay. In this case, you have an electron pair, a pair of electrons in anion vacancy. So you can think of it this way, that you have an anion missing, okay, and from some site, and in that site, okay, there is a pair of electrons. Okay, so that would lead to something like an F prime center. This is found in calcium fluoride in CaF2. You could have an Fa center this would be an electron and a K plus. An example of this, an electron and a K plus ion in Na plus vacancy in NaCl. So this is a case where you have the sodium chloride structure, and in one of those sites the sodium atom is missing, and it's replaced by a K plus ion and an electron. So then there are things like M center, which is pair of F centers of nearest neighbors, F centers, okay, and so on. You could also get things like R centers and F centers in perpendicular plane in 1-on-1 planes, and ionized centers, and so on. Let me just once again show the nature of the F center. Okay. So if you take this sodium 1 plus delta, okay, so if you take the sodium 1 plus delta, now there are some excess sodium atoms. Okay, now those sodium atoms will get ionized. So let us show the F center in NaCl. Okay, so I will just show you how this F center is formed. Okay, so you have some excess sodium atoms that will get ionized to sodium plus, okay, which will stay on the surface, and an electron, and this electron will actually go inside the crystal, and it will occupy an anion site, and it will give the F center. So this electron will occupy the anion site, occupies Cl minus site. Okay, and this is the color center that you get. Okay, so the way you get an F center in NaCl is, it's actually this even though it looks like excess sodium, it's actually the excess electrons that are produced due to ionization of the sodium. Okay, and those occupy the Cl minus site. Okay, and I should also mention that you can get things like V centers. So V center. Okay, so this is basically a Cl2 minus. So instead of a chlorine ion, you have something like a Cl2 minus in one of the site, and that would be a V center. And again, so these color centers are actually very, I mean, they are quite widely seen in ionic crystals, and they are responsible for some colors in these ionic crystals. Okay. So if you take a perfect sodium chloride, you will just see it colorless, you will see it white. Okay, but in the presence of these, if you have these defects which are called as color centers, then the sodium chloride crystal will actually look colored. Okay, I do not want to spend too much time discussing the different kinds of color centers. okay, but it's good that you are aware, it's good to be aware that there are such things in these crystals, okay. So I will conclude this discussion on point effects. In the next lecture I will change tracks and start discussing about line defects. Thank you.